Hey, math people. Lecture 3 of Chapter 1 of Calculus 1. This is the last lecture of my little limit run here. We're going to be looking at continuity. We looked at discontinuities in the last two chapters. This one will kind of softly define continuity, at least in the landscape of like a Calculus 1 course, and then justify continuity. We'll create cases where we kind of like create continuity, and then we'll use a theorem that is like a nice immediate use theorem to the assumption of having continuity within a graph. All right, remember, this lesson is for you, Ahmed, whatever your name is. Use the timestamps, right? Make this video useful to you. Also remember to be patient with yourself. Pause when you need to. You can do this. Let's math. All right, so this one's fun. Just a good little opener. Draw a curve where the limit and the function evaluated at whatever that value you're approaching is a, so we'll say 2, all right? So draw a curve where the limit as you approach 2 is the same thing as f of 2. See what that looks like. Here's my drawing. Looks like this. It's forcing a connection. When you have the limit as you approach a value as the same value as the defined moment, that's how we get continuity. There are more formal definitions of this, but for differential calculus or calculus 1, this is adequate. If I ever want to justify continuity, this is how we do it. We show that the limit coming in from the left is the same coming in from the right. We say that the function evaluated at a is defined. And then we also say, well, the limit is equal to that defined value. When this happens, then we're continuous at that moment. Let's show an example. So looking at the graph right away, would you say this is a connected graph? Hopefully you said yes, or you're possibly blind. It's connected right here, right? We see that we have a connection. It's got this little corner, but that's not an issue. So what we would like to do is justify. I say prove, but I think justify is a better word. Justify that this is in fact continuous. So I'm just going to show you how that justification works right now. So I have shown that f of 3 is defined. I've also shown that the limit as you approach 3 is equal to 8. What some teachers may require is that you say the limit coming in from the left is 8 and the limit coming in from the right is 8. Therefore, the limit as you approach the value is also 8. In my opinion, that's a bit much, but some people do require that. So just be mindful of that. But here's my bottom line. If the function evaluated at the input is 8, and we know the behavior by the definition of a limit coming in from the left and right is also 8, then therefore the function is continuous at this value of 3. It's continuous and the output is 8. All right, so if we were to look at this graph, does this appear to be connected? No. No, it does not. So we're going to go through the same exact logic here, and we're going to see that, well, if I attempt to evaluate f of 3, what I would do is, and I didn't talk about this in the last one, but you plug it into the one with the or equal to. So if I were to plug in 3 into this bottom one, the natural log of 1 is none. That's like my little chime to help students remember that. So we get the natural log of 1 here, which is just 0. And then if you take the limit, well, it just doesn't exist, right? If you were to approach, and that's enough. That's enough to show that this is not continuous. Really, this is the big kicker right here. But if you were to take the limit coming in from the left, you would get 0. If you were to take the limit coming in from the right, so that's the cubic, you would get -1. That is a mismatch. So, the limit does not exist. And then that doesn't meet one of the criteria, right? The criteria being, both. It fails 1 and it fails 3. So limit does not exist. Therefore, our function is not continuous at 3. Okay, so feel free to pause it here, but I have a few piecewises that you could graph if you'd like. Which of the following is not continuous? What I would advise you to do is to do these algebraically. If you want to look at the graph thereafter, feel free. But feel free to pause. 3, 2, 1. Okay, so I personally keep it nice and simple with this. Now, let's also take a further step back. There is a very, very rigorous definition of continuity. And if you're thinking this isn't anywhere near what I'm learning, you're probably in some real analysis course, and this is not for you. This is for like a Calculus 1 student. All you need to show, in my opinion, is that, okay, the function is defined. It's equal to the limit, which is implied that the limit exists coming in from the left and the right. It's the same value. Both of these are 1. So since the function is defined and the limit is defined as the same value, it's connected and it's continuous. I'll just show one. I feel like this video is going to be a little shorter. So how we do piecewise functions in Desmos, we just do 2x plus 3, so that's just the top. And I'm just going to say when x is less than 1. So it's nice, it's satisfying to see what these look like. And if I look at x squared plus 2x plus 2, this is when x is greater than or equal to 1. We see that nice connection. Now, it's kind of cornered off. You can see the slopes don't match, and that's eventually going to be a conversation, but not today. If we look at like the next one here, so we're looking at the same function, 2x plus 3, but this time around we're just greater than 0. And then we're looking at the same function below, we're just less than or equal to 0. We don't see that same idea. We actually see a jump discontinuity here, right? The limit does not exist because we're approaching 2 coming in from the left, we're approaching 3 coming in from the right. So we don't like that. We say that the function is defined, but not necessary. This in itself is just enough because it doesn't meet one of the criteria, so therefore it is not continuous at 0. Similar logic can be made for the next one. Function exists, so feel free to explore that, or the function's continuous at 1. Feel free to explore that on your own. Okay, now what if we want to create the continuity? This is kind of fun. So like, I like the visual for the first one. We're going to be playing this game of find the k value. So I have this line when we're greater than or equal to 2. And then I'm going to have some control over the slope of this line, which I'll show you once. I'll zoom out in a second. And I have this parabola when we're less than 2. So here's the game. It's pin the tail on the donkey or pin the line on the parabola. What we're doing is we're just trying to find this sweet spot moment where they, somewhere over here, right? Where they connect, right? Clearly not connected, clearly not connected. It's somewhere in between 0 and 1. We just don't know exactly where. So that's the game we're going to play. And then within the second one, it's instead of pin the tail on the donkey, it's pin the point on the line. You'll see this in a second. What if I had x squared minus 9 all over x minus 3, and then I just have some point, which is going to be 3 comma k. So I have this line, which I'll just spoil some of the fun here. It's got a hole on the x value of 3. And all we want to do is we just want to figure out where must this point go to fill in the hole, right? I mean, this one's a little more obvious visually, but that's the game for each of these. So I'm going to go ahead and just show the algebra for the algebraic solve of them, rather than just like blindly guessing or looking at a graph. You set them equal to each other, right? You want them to have the same outputs. So you set them equal to each other, and you may be thinking, well, wait, I have an equation with k's and x's now. What am I solving for? Well, you know that the moment they switch is at an x value of 2. So you plug in those x values of 2, you solve for k, you get a half within the first one. So, if I wanted to verify that, because it's satisfying to see it click, I bring it down to a k value of a half, 0.5, and snap. Pin the line on the parabola. And then same story for the second one-ish. Actually, the solve is a little different. You can see that you can pluck out the hole by factorizing the numerator and canceling out the x minus 3's. So that's the issue, is the hole at 3. So you just want to figure out, well, what must the output be in order to connect it? Well, you just plug the 3 into what remains, and in which case it's just 6. 3 plus 3 is 6. And that one was very obvious, like visually, right? It's literally just trying to figure out when to get this point on the line, and it's when we're equal to 6. So bottom line on this one, I factored the top, canceled the x minus 3's, which were the issue, right? 3 minus 3 is 0. And then I just took that remaining expression and plugged in 3. Nice. All right, looking at the second half here, we're looking at intermediate value theorem. So let's just say we have continuity. If we have continuity, we can say a cool thing. And I'm going to show you the math, but I'll explain the intuition thereafter. If we have continuity on some interval, then f of x takes on all values between f of a and f of b. This is much more logical than you think, and it has to do with staying hydrated. Sort of. Let's just say I have my water bottle and I have no water in it. Right now, I need to be a little more hydrated. I'm like right here. If I were to fill up my water to, I think this is 20 ounces. I don't know. I could be wrong. But let's pretend it's 20 ounces, right? And it's at 0 fluid ounces, and I fill it up all the way to 20 fluid ounces. I would have hit every fluid ounce in between 0 and 20. At some point, it would have to fill up to 4 fluid ounces as I'm filling up the water. At some point, it would have to fill up to 10. At some point, it would have to fill up to 18 in order for me to get to 20. Every value from 0 to 20 is hit when you have a continuous function. Right? You're driving a car. You're driving, you eventually make it to the speed of 60 miles per hour. You hit everything before that. You didn't just flip a switch and you went from 0 to 60 in an instant. That didn't happen. If you have continuity, you hit all the values in between. This is asking, is there such a value c where f of c is equal to 2 between 0 and 1? So what this is actually asking us to solve, in some ways, is can you solve the equation 5x to the 4th plus 3x squared plus 1 equal to 2? So what we do is this. We make some sort of statement on continuity, because that's the important piece. If you don't have continuity, this just doesn't work. All polynomials are continuous, so there's no issues here. We're just going to say the function's continuous from 0 to 1. You don't have to prove that. So then this implies that we can use the intermediate value theorem. I'm not solving this equation. This is way too much work. No thanks. All right, so what I did was I plugged in the lower bound of 0. That's a very easy plug-in. You plug in 0, you get 1 as the output. I plugged in 1. 5 plus 3 plus 1 is 9. So what this suggests is that every value in between 1 and 9, I touch. So therefore, since 2 is in between those outputs, there must exist some c where f of c is equal to 2. It's sort of like a logic-y puzzle. It's I would say with problems like this, as soon as it's like you see it when you see it, which is maybe not the most satisfying thing to say, but I'm going to show you the big thing is that you build a conceptual basis first. So I'm going to go ahead and graph this. What is the curve? Plus 3x squared, and then plus 1. Okay, so if I graph this, and I really only care about this from 0. Well, first off, I want to show you that polynomials are continuous for all real numbers. There's no issues with this at all, right? But I only really care about this from 0 to 1. And then I want the or equal to's because I want to show you the outputs at these moments, right? So, okay, the output here is 1, right? I'm pointing with my hand. That's this right here. And then the output over here is 9. So that's this output right here. So since it's continuous, I hit every value from 1 to 9. That's all IVT is. Here's the thing about math. Sometimes you see stuff like this, and it's like it feels like your eyes are crossed, and you're like, what's going on here? Like intervals, function, like notation. I'm gonna pass. There's some intuition here that is accessible, right? So when do we actually hit a value of 2? We can just say y is equal to 2. It's at this moment. It's at 0.48838. I'm sure it keeps going. I don't care about that because that's not what it's asking for. It's asking, is there such a c value where I hit this? And the answer is simply yes. There exists a c where f of c is equal to 2. Where is that c value? It's here, and I don't care about that. That is not what this question is asking. All right. Yeah, go ahead and read this one. I'll read it. Verify that IVT guarantees there exists a 0 from 0 to 2 pi on this cosine graph. So having a 0 is, do I touch the x-axis? Does this graph touch the x-axis from 0 to 2 pi? Feel free to pause. Feel free to try to fit. So feel free to pause here too. try to fit the mold of this argumentation if you'd like. Some AP teachers will be pretty particular about that, by the way. So 3, 2, 1. If you look at this one, trig functions are continuous. Trig functions that are sine and cosine. Tangent, you got to be careful of. Actually, all the other ones you have to be careful of. But just do that soft check on continuity. Cosine's fine from 0 to 2 pi. IVT can be applied. If you plug in 0, you get 3. If you plug in 2 pi, you get -3. So is 0 somewhere in between -3 and 3? Of course it is. So therefore, there exists some C. And I'll just show this one, and then I'm going to probably stop showing the graphs for these. For sake of brevity, I encourage you to use Desmos to verify a lot of these. So, and I'm just going to do it this way too. X is equal to -3, X is equal to 3. You know, is there such a moment? What? Whoa. Ignore that. Those were the outputs. X is equal to 0, X is equal to 2 pi. So we want the inputs, the X values, not the Y values. Here we go. So is there a moment where we touch the X-axis? There sure is. It's at pi, and this one's actually kind of easy to solve. But we are not doing that. That's not the point. We're really just exercising like an application of continuity. Like continuity is like really a nice thing. All right. Feel free to try out this next one. More the same rhythm. So 3, 2, 1. Exponentials are fine. Those are continuous throughout their domain. F of 1 is 1. F of 3 is 9. Turns out the number 8 exists between 1 and 9. So some teachers, again, are very particular about this language and like stating the continuity requirement. Like, you can only do this because of continuity. And if you don't have the word continuous within your argumentation, like if you're on the AP exam for sure, then you are not getting the point. So just be mindful that continuity is required here, because otherwise if it just hopped, right? If it just jumped up, so consider like, I don't know, absolute value of X over X. You know, if I said between, no, we'll do it this way. Between X is equal to 2 and like X is equal to whatever, -1, do I hit the value of 0.5? No, right? This is not continuous, right? You're -1 the whole time here, and you're 1 the whole time here. Even though the outputs go from -1 to 1, and you're like, oh, okay, yeah, 0.5 is in between -1 and 1. It isn't continuous, and it jumped over that value. So you need the continuity piece. All right, here's a fun power round. What would be a better interval? So for each of these, the intervals suck. And they all have bad intervals for some reason or another. This is just a do you follow me exercise. So I'm going to give you just another 3 seconds to just pause and play around if you'd like. 3, 2, 1. Okay, looking at the why can't IVT cases. Looking at the very first one, we see x squared, and there's no issue with x squared. This is a continuous function from -infinity to infinity. What's the deal here? Look at the interval. If we see here the intervals from -1 to 1, that's the same output, right? Because we consider that the parabola is symmetric about y-axis, right? About the y-axis. So that's an issue. We're essentially effectively saying we hit every value from 1 to 1, which isn't very useful. So what we can say instead is something like 0 to 1, right? Because if we consider x is equal to 0 and x is equal to 1, what are we trying to hit? We're trying to hit a half. We hit that half somewhere in between. We hit it right around here at like 0.7-ish, right? But if we were to have considered from -1 to 1, I mean, let's really think about that, right? Doesn't give you a lot of information. Looking at the second one, I see 1 over x, which we've been making this assumption every time of like, oh yeah, that function's continuous, that function's continuous. 1 over x is not continuous. However, well, okay, and it's also not continuous on this interval from -1 to 1. So that's a huge issue. You cannot apply, because anything goes, right? You can fudge the scenario to pretty much any case you want to if you don't have continuity on the inside. However, you do have moments within 1 over x that are continuous, right? So with that said, I have to just be smarter about this interval. So if I were to graph 1 over x and consider when x is equal to 1, I want to contain 0.123. So I want to go as low as, Where's 0.123? I want to go down here, right? I want to go down to like 8. Oh, that was actually perfect. I want to go down to 8.13. So I can just stop it if I wanted to at 9, if I wanted to cut it close. That's the number 9. If I wanted to keep going, I can go to 10. That's a little safer, right? Because if you consider f of 1, that's just 1. If you consider f of 10, that's 1/10, which is 0.1. And 0.1, between 0.1 and 1 is 0.123. So a better interval from 1 to 10. And then the last one, the cubic is good to go, right? It's just continuous, it's polynomial throughout its domain. So do we ever hit pi? Almost never do we ever deal with pi within polynomial scenarios, but we do hit pi at some point. From -1 to 1, though, that's no good. Consider that we're just going from -1 to 1 within that interval, and that is not going to cut it, right? We have this as my -1 to 1 as my interval. So we hit everything from -1. You have symmetry here. We hit everything in between. But pi is all the way up here. Pi is like here-ish. So it doesn't really matter which one we change. Maybe we change this. I changed the lower bound and upper bound. So I just kept this 1 here, and I just made this a 2. And then sure enough, where is pi? Y is equal to pi. I hit it within that interval. I hit it at 1.46, which is contained in between 1 to 2. All right, and here's a little comic thing I found from this guy. I used to be as tall as you. I know the intermediate value theorem, Dad. Yeah, because if you're 6 foot, at some point you were 2'3" or however tall he is. I don't know. Okay, that's continuity and intermediate value theorem math on.